All right. So as I said earlier, welcome to shading and lighting. All right, so today we're going to be working on rendering. Lectures are broken up, well actually our class is broken up into four main categories. Rendering, learning how to render. There is lighting. Lighting's broken up into several parts. There are materials, the different properties, what makes an object look like it does to us, and how do we identify it as plastic, wood, metal, concrete. We take away the color, we take away the pattern on it. We still are able to identify certain material properties. And then we go into texturing. Almost half of our class is texturing based. But understanding how things work up to the texturing point is very important. Some of the projects, starting with project 4, will be carried on into project 5, 6, and 7. Actually, yeah. Carry on into project 5, 6, and 7. You'll be reusing them to the next step. You're going to light an environment. You're going to add materials to it. You're going to do an animated moving camera so you understand how rendering with animation works. And we're also going to texture it. But today we've got standalone scene that is just used for basic rendering. All right, file management. I don't know if anybody's ever talked to you guys about how to manage your files on your computer. But it's really important when you get into high-end software. By high-end, I mean stuff that is usually used in a professional pipeline. Anybody know what the Mac OS is built on? Other than Mac OS and iThing. Built on Unix. Unix is that thing that runs the internet underneath all the pretty graphics we see. It's a very powerful old OS. Apple chose to build it on there because it is probably one of the most stable systems that's out there. In its bare bones core, you do not even need a graphical interface. Anybody here ever use DOS? Yeah, probably many of you are way too young for that. So us old people, we know that. Not you that you're old. Yeah, DOS, it's a non-graphical interface where you have to type in your commands. The thing about that is it's really fast because it doesn't have to show you pretty stuff. It does a lot of stuff, but you don't get to see it until it's done. The thing about the Mac OS being built on Unix is it uses a lot of the Unix file management protocol, which means it puts stuff into hidden folders for you. All invisible to the user so you don't get frightened by weird names and like file names that are this long with all kinds of weird stuff in it. All right? It just gives you nice, pretty stuff. Linux is built on Unix. Linux is just a version of Unix that is not ashamed to say, I'm on Unix. Anybody here ever use Ubuntu? No? If you have an old computer and Windows runs like crap, put Ubuntu on it and it will run like a new computer. It won't be pretty. I mean, it's got a good interface. It's very graphical. It looks and feels like a Mac or Windows, but it has a lot less what we call overhead. There's a lot less little programs and apps running in the background doing bouncy things and animation and making you wait for commands to happen. It does stuff. All right, why am I getting on this? Okay, I'll get off my soapbox. But the reason is because in RenderMan, if you have a space in any of your file names, your renders will fail. If you use a special character like an asterisk, a slash, a forward slash, a backward slash, a caret symbol, parentheses, the only thing it will allow you is an underscore or a dash. So if you are naming your files and your folders, stay away from spaces. Put an underscore where there's a space. Okay, having said that, there's a way that we can check it when we get into RenderMan to see if it'll fail. It's going to be a little bit of a manual process to look at it. But here's the usual situation is, you download the files, everything we give you is going to have underscores in it or no spaces. If you want to run words together, the protocol is usually capitalize each word. So if you've got my files, like M might be capitalized and F for files would be capitalized, run them together. Or you go my underscore files. Dashes are okay, but try to avoid them just because I don't trust them. I don't trust Maya. You will learn not to trust Maya also. If you trust Maya, that's your first mistake. It will bring you nothing but heartache because it will crash. So, no special characters. This one right here, exclamation point, that's called a bang in Unix. That is a very big command to do something right now. So RenderMan has no idea. You just put that in there and it goes, nope, it stops. All right, so you download your stuff. You want to put it in a subfolder because you want to get it off your desktop or get it out of your downloads folder. Make sure whatever folder you put it into has no spaces, no special characters. It's easy to forget because you've got, you're good, you make separate folders for each class. You go shading and lighting. So maybe you put shading, space, and space, lighting. Or maybe you put shading, ampersand, lighting. Ampersand, no, bad. Ampersand is the little thing that looks like a G clef in music, only it's backwards. All right, that's bad. Use underscores. You guys all know what underscores are, right? Okay, good. Actually, even in Windows, if you are a Windows person, you should be doing that anyway. Spaces are still counted as a character, but since they have no visible input to the user, they can be really tricky. Another thing that you really need to do is you launch Maya first, then you set your project, then you open your file. I know the real temptation is to just double-click on the scene file. But unless you set your project, you will be missing information in our scenes. Because we will have images linked to what's called a dome light outside the window. Stuff will show up blank. You won't be able to see it. It'll fail. It'll change the way your lighting looks. Later on, your textures will be missing. It just creates havoc. Another bad habit to get into is work on all your stuff on the desktop, link it up in Maya, and then you move it. Once you move it, Maya doesn't understand where those files exist anymore. And it goes crazy and fails also. So, you guys know about the project folder structure in Maya, right? It's got a whole bunch of folders. The most important folders in there are your source images folder, your scenes folder, your images folder, because that's where RenderMan's going to try and put all your rendered images. And RenderMan's going to create its own folder called RenderMan and keep all its information in there as well. If any of those things are missing, stuff won't work. That's why it needs to have that. It needs, when you set your project, it's going, hey, all the information for this scene can be found in this set of folders. It's like a little database package. Makes everybody happy. Right, questions? All right, probably make a little more sense. If you never dealt with any of this before, it'll make a little more sense when we actually get into working with Maya and RenderMan. Okay, breathe. Yeah, a lot of information, I know. First day is kind of always like that. All right, so we're going to talk about rendering now. Kind of give you the intro to rendering, what it's about. First off, in order to make anything visible, whether you're in CG or in the real world, you need three basic elements. One, you need something to act as a sensor, something to perceive the phenomenon. Your eyes, a camera, any other recording device. We need light. Without light, we as humans would not be able to see. And without an object for light to hit, you're not going to see anything. Now, in CG, we also need one other thing. That is something called a material. How many of you guys have modeled and all of a sudden your object turns green? Yep. What happens is that loses the shading, what's called the initial shading group, that Lambert. It loses the connection to it for whatever reason. If you try to render it out, it will show up black, empty, not there. So what you have to do is reassign the initial shading group, Lambert 1 to it, you're good to go. But in the real world, every object has a material already. It's a self-contained little package. So, what we are doing is we are recording things by rendering. But rendering doesn't just mean CG, lights, camera, action, no. Rendering is also a term used in fine art. Got anybody here? You guys have Art 1 yet?
Yeah.
All right. We talked to you guys about rendering.
Yeah.
What is it?
This line to make the image look clear.
Make the image look clear. Okay. What else? Anything else? Yeah.
Producing an image or media.
Producing an image media. Yeah.
Refining it.
Refining it. Yeah.
To test how the light interacts with the surfaces.
Okay. That's how light interacts with the surface. Yep.
Light and shadow reflection.
Light and shadow reflection on the surface. Yeah, that's pretty much what it is. Everything we are trying to define, even in fine art with pencil, with line art even, you are trying to define light and shadow and how it reacts to the surface. Where does the light come from? That's going to be brighter than where the light doesn't come from. That's going to be your shadow. Absolutely. So it's light and shadow and a reaction to a surface. And that's basically what we just described earlier, too. Three things. You've already got eyes. You're describing light and shadow with ink, with canvas, with paper, with pencil, whatever your medium happens to be. And you're trying to define how that light hits an object, a surface. And in art, if you're drawing, we need to define what kind of surface that light hits manually. If you're a photographer, you set your exposure right, your color balance right, your depth of field right, to focus in on what your subject is. So here, 18th century artist Frederick Leighton, they were fascinated with cloth and folds because there's a lot of shadow. There's a lot of light. Negative, positive spaces, how does that define what we see with our eyes? All the way over here to kind of a what we would consider kind of a non-traditional medium. This is Samir Strati. He's a mosaic artist. He uses nails. He did the Da Vinci self-portrait with 500,000 nails. Right? Roofing nails, drywall nails, copper, zinc, brass, white, black, gray, whatever he needed, he used. His nails would be equivalent to what for us in CG? Pixels. Yes. All those little tiny dots of light that make up our surface. Pixel. So when you complain about mouse keystrokes, oh, my finger hurts, you could be hammering your pixels into the side of a wall. Getting carpal tunnel and stubby fingers from hitting it with a hammer. All right. So let's go to what is rendering in 3D. For us, we're taking our beautiful polygons that we modeled with. And polygons are what? What are polygons?
Shape.
Shape? Okay. What is that shape made of?
Triangles and
At least 3 sides.
It's triangle. At least 3 sides. Yes. That is the smallest unit of a surface. Because if you have 2 points, what do you have? A line. If you have 1 point, what do you have? A dot. Yeah. So, a surface needs at least 3 points. Now, in modeling, we use quads for the most part, right? But don't think that everything is quads, because when you hit the render button, everything gets converted to triangles, called tessellation. So we're convert our polygons to pixels. Each one of those tiny little dots represents some kind of point to define our polygon. Now, in rendering, we have, for the most part, 3 different ways to render. And I'm not just talking computer animation, film. I'm talking about gaming also. Same principles apply to gaming. But they all utilize different ways to render. So we've got 3 different ways we can render: software rendering, hardware rendering, and vector rendering. First off, let's define what they are. What would software rendering be?
does it within the program.
Does it within a program? Okay. Program such as?
VLC, Studios, Adobe Movie Maker.
Okay. All right. Do you render out of those? Well, are they just players or are they creators?
Oh, it's not like I'd say mismatched, but for the creators, can't you render with those?
You can.
Okay.
So something like After Effects.
Yeah.
You could make a movie and play a movie. But you are rendering it, yeah. So software would be inside the computer. Give me other programs that you could render out of.
Arnold.
What?
Arnold for Fire.
Arnold?
The Adobe.
Yeah, Photoshop maybe. Photoshop uses stills for the most part, but yeah, stills. Yep.
Cycles of Blender.
Blender?
Yeah.
Yep, Blender.
Maya has its own software.
Maya does.
Renderman.
RenderMan. Yeah, the obvious, the elephant in the room. RenderMan. Yes. And a couple others. So yeah, we could go on and on and on and add programs that create finished final versions of images or sequences. But for the most part, when we think of it in 3D, we usually think of either Maya, maybe 3D Studio Max, maybe Lightwave, whatever else happens to be out there that renders. Blender, anything else. All right, hardware. What is hardware?
External.
External. External to what, though? Let's be
Your program on your computer.
program or computer. Yeah, possibly. Yeah,
And it might be your computer or any like device.
could be your, yes, it could be your computer or any device. Yep.
It's the machine, not the program.
Machine, not the program. So hardware would be your physical graphics card, your phone, because your phone renders out stuff for you, right? When you turn it on, you've got a display, you've got a GUI interface, it's touch sensitive, you move stuff around, you touch, you swipe, you double tap. So specifically, yeah.
So how would your hardware do it without using software?
It would do it with, here's the kind of catch-22 with it. There is software embedded in your hardware, but it does not require it to be read all the time. It exists kind of like, think of it kind of like your brain. When you want to do something you've already got information on, you can do it quick. If you want to do something you're not familiar with, you got to go research it. You either go to your phone, you go to your computer, you look online, you try and figure it out. That would be equivalent to software. Hardware would be, I got the information here, I can act on it right away. But it really is software embedded in the hardware. It's either embedded in code that is static, which means you can't address it, or it's dynamic, which means you can update it, like flash memory, where you can go in, update it, make sure it's current, so next time it'll run fast. Your Macs, for example, use what kind of hard drive? Solid state. They don't have to spin a little disk and read off of it. So the information is readily accessible a lot faster than being read off of a spinning disk. Because then it doesn't have to spin, and then the head has to find the information, and it has to decode it. It exists there, it can address the memory, read it, go. So let's put it into something that would be equivalent to what would be relevant to us. We've already defined software rendering as kind of Maya, Blender, 3D Studio Max, Maya, RenderMan, Mental Ray, V-Ray, Any Ray, iRay. So hardware. What is it? Camera, computer, phone. Okay. Exactly. How about things you interact with all the time? So most of you are, I would hope, at least have played a thing called a video game. Gaming? Yeah, you may have heard about it on the interwebs. All right. Real, for us, hardware rendering is equivalent to real time, where all of the work is done on your graphics card for the most part. You don't have to wait for something to process. It's already built in, it's inherent. So for us, Maya does real time. Not well, but it does it. Unreal, Unity, Substance Painter. Substance Painter's got iRay built into it. You put a texture on, you can see it show up right away. The holy grail is everything hardware rendered, because then you don't have to wait for it. But we're not quite up to that point where we can get film quality, even game cinematic quality. That's still being rendered software, just because you want it to look better. There are certain limitations to hardware. For one thing, you can't do ray tracing and explosions and fluid dynamics and particles and all that stuff. That takes a lot of memory, a lot of speed, a lot of processing power. Generates a lot of heat. You pretty much need nitrogen-cooled computers so that they don't burn up. All right, vector. First off, what is a vector? Yeah.
I know when it's in Photoshop, it was like
Okay, but what? Like, what are those vectors? Curve. Okay. Connection. Curve. Anybody here of a program called Adobe Illustrator? The Illustrator uses vectors. In particular, what they call Bezier curve. Now, with 2 points, you can define it with a straight line, a curve, or the Bezier points allow you to make that curve into kind of an S-curve. Or you can define where it's going to curve a lot better than just saying, oh, you're a 30-degree arc, or you're a straight line. The nice thing about vectors is you can make vectors into a surface. And you're defining that surface with points rather than pixels. You're doing it with math. The advantage to that is you can make it scalable without losing any resolution. Because all you're doing is 50% smaller, 200% smaller, 300% bigger, 400%, and it just does the math and it says, oh yeah, your curve is going to look like this at that size. So Maya does do vector rendering, Adobe Illustrator, and also CorelDRAW. So what's the difference? Software usually occurs on your CPU, your central processor. It has to run a program, an application, in order to process that information. It takes time. We're not restricted to the graphics card, although the graphics card is used. Don't be fooled into thinking, oh yeah, hardware rendering real time doesn't use, the CPU. Well, yeah, it does. They just steal it, whatever it needs. Produces very high quality images because we have to wait. There's the downside, time. In production, time equals money. The faster you get stuff done, the cheaper it is to produce. Hopefully, you're efficient. You get paid more because you are a time lord, which is basically what you need to be. Right? But it is more time consuming. Hardware occurs mostly on the GPU. As of now, the quality is not quite as good as what we wait for in rendering, software rendering. It's very good. A whole lot better than it was 5 years ago. We're still about 5 years away from getting really good, full-blown, perfect renders ready for film. A lot of studios are utilizing, whenever they can, real time. All right, faster. There are some limitations. First off, there is a mesh format called subdivision surfaces, not taking your normal polygon surface and subdividing your mesh. No. It was called sub-D. Pixar dabbled with it way back in one of their shorts. Anybody here ever see a Pixar short called Jerry's Game? Old guy playing chess with himself back and forth. Right? That whole scene was done with subdivision surfaces. Subdivision surfaces were kind of seen as the savior because they were a compromise between NURBS, which is mostly curves and making surfaces with curves, and polygons, which are, three-sided surfaces that you edit the mesh directly. It was kind of seen as the love child between the two. But the problem was there was a lot of overhead in it because it tried to do two things. But graphics cards got better, memory got better, so it kind of fell by the wayside. It was way too slow and clunky to use. It looked good, but really not user-friendly because it was move, wait, computer had to catch up. Move, wait, computer had to catch up. So they toyed around with it, but that was pretty much dropped. In fact, I think Blue Sky used it for, the first Ice Age. They used it for part of it. Again, polygons just, graphics cards, memory got better, and there was just no reason to support it. I don't even think you can find it anywhere in Maya anymore. Used to be a plugin you could you turn on and play with. Nobody uses it. Now, one of the things that we usually have a limit on in real time or hardware is what we call lights. Because lights can be one of two kinds of lights: a static light or a dynamic light. What's the difference between static and dynamic?
Natural,
Movement.
Being natural or artificial.
Static is still.
Natural or artificial what? I heard somebody.
Static is still.
Static is still. Okay. Dynamic changes.
Is dynamic light like non-static?
Only, yes it is, with limitations. Yeah.
I think like the light device lights where you have a certain light source and it shows on the bounce back from the light source. So it
You're
should-
kind of all correct in that. Here's an easy way to remember. In this room, around the perimeter, on the walls, we have no moving shadows at all. As of now, that would be static light. Once I go over and interact with it, now I've got a shadow on the wall. This is dynamic. So static light in a game is really, would be things that you would have maybe an environment. You walk into an environment, it's got light on it. All right, it stays the same pretty much. As long as you don't have a character interacting with it, we can do what's called bake that lighting into the texture. That way it looks like it's lit. It is lit for all intents and purposes, and we don't have to worry about it. But once you get a character coming in and interacting with that environment, it turns to dynamic. And what you want to do in a game is have as little calculation as possible. So you don't calculate all your lights as dynamic all the time. That's a waste. You'd rather have it for collisions, particle effects, fluid dynamics, special effects. You don't want your character walking through a wall because you're busy trying to calculate the light instead of where the character is in relationship to the environment. Yeah. So the thing is, we usually limit the number of lights. Maya's got a limit of 8 lights that will support at one time. You make light number 9, light number 1 turns off. So you can only have 8 going at once. Some game engines have limitations. Depending on the game engine, it's going to change. Shadow support. Every time you have a light, unless you tell it otherwise, it will create a shadow. Now, there are different types of light. We have lights that simulate the sun, light that simulates bare light bulbs, light that simulates a large surface. For example, like if we took the overhead fluorescent light, that box, and looked at that as a surface, there's a big, broad, section of light coming out of that. We've even got the projector screen, which could be considered a source of light because I've got the light from the projector shining on it, but it creates enough light where I can see my hand from the light bouncing off of it. So certain lights will behave in different ways. For example, there's a light called a point light, which behaves like a bare light bulb. Bare light bulb illuminates how? All directions. Omnidirectional. Unless you've got a special light bulb. That like a floodlight. That might be projection. Our projector, it projects light in one direction. It's a little different. But a bare light bulb usually illuminates in all directions. If it illuminates in all directions in the real world, it also casts shadows. If it casts shadows in all directions, great for the real world, not good for gaming. Because you don't want to calculate shadows in all directions, only from the axis you need it. So a lot of times they will have the ability to limit shadow casting from a light bulb, like a point light or a bare light bulb. So it limits it to just one axis, where you need a shadow from. Cuts down calculation time. All right, and there's another light called area lights. Area lights, those broad surfaces. Thing about an area light, it can be big, it can be small. The size of that light changes how shadows behave. So for example, if I have a very small light a distance away, I get a razor hard shadow. As the light gets bigger or the surface gets closer to the light, what happens to the shadow?
Blurry?
Yeah, it gets blurry because the apparent size of the light gets bigger. It's apparent because it's based on distance. The bigger the light, the softer the shadow.
Does this also count for like natural light and
This
artificial
is
light?
exactly how natural light works.
Okay, because like the
And-
sun or light bulb to like produce like different kind of shadow.
Yes, absolutely. So everything we talk about is usually based, our reference is the real world. And everything we do in CG, we try to mimic. So, and that's kind of what I want you guys to think about is, this is what I get in the real world. How do I do this in CG? Or what's the best way to do it? Now, the thing about CG or real world is, you may be able to use a single light and have it illuminate an entire room. Whereas in CG, we may not get that much bounce. So we have to add in other lights to account for loss of energy. Make sense?
Mm-hmm.
All right. Questions so far? Does that kind of make sense? Just kind of laying the groundwork for how rendering is going to work. Because everything we talk about, all this calculation, that's what the renderer is trying to do. It's trying to do as best as it can to mimic the real world. All right, vector rendering. We have a couple formats that are friendly for vectors. You've got the Adobe AI format. You can actually use Maya's vector renderer. You have to turn the plugin on. You can render out vectors. You can get line work, line art, tune outlines. You can get wireframe, and not the crappy wireframe you get when you do a play blast. It's like takes your curves or it takes your mesh and actually uses vectors to produce really good looking outlines. So Shockwave or the old Flash format, AI, PostScript, nobody uses PostScript unless you're doing print work. And then scalable vector graphics, SVG. They are popular on the web because you can scale them up, shrink them down, and they do not lose quality. Why don't we do everything like that? Well, certain textures don't lend themselves to being turned into vectors. For instance, look at our floor. That would be hard to turn into vectors because there's so much subtle gradient between all the stripes. Granted, there's a lot of filth there too, but there's a lot of gradient that's hard to define when you're talking about points and curves. It's a little easier to smudge some pixels. All right, software rendering, that's what we're going to be mostly focusing on. We are going to do some hardware rendering when we get into doing some animation. Maya versus RenderMan. Maya, it's got the advantage of being built into the software. Trouble is, it is old technology. It's been around since the early 90s. Maya started out as a scanline renderer before ray tracing was introduced. Scanline means that it did row by row, pixel by pixel, and then it went and started rendering row by row, pixel by pixel. Works kind of like an old dot matrix printer that just went. You guys probably have no idea what that's like. It's like a crappy inkjet printer. Right, ray tracing wasn't introduced until the mid-1990s. It was kind of a retrofit into the software. Maya supported it, but didn't really go beyond supporting it with the basics. One thing they did do from the beginning with scanline or software rendering was this thing called IPR. Every modern renderer uses IPR. Interactive photorealistic rendering is basically just an update that constantly runs, so if you make a change, it automatically updates in your render. It's a really great thing to have, but it's still slow. Because we still have to wait for it to process. Yeah.
Is there any way we can speed it up?
You can speed it up, but the quality will degrade. So you have a threshold of, we usually use IPR for quick positional reference. Like put my lights in, do my lights, so my shadows match where my light is in my reference. Everything looks pretty good. Once you get things dialed in, you're going to start rendering higher quality. But IPR is going to let you see the shadow, the position, the softness or hardness of the shadow. It's going to let you see color. It's going to let you see ray tracing effects. It's good, but like I said, the cost is very low quality to be able to have that interactivity. Now, ideally, real time, you would move something, it would be done before you even went your eyes. But we're not there yet, unfortunately. But IPR is the next best thing. And RenderMan runs pretty good. The nice thing about RenderMan, it works a little bit like Arnold, where the longer you let it go, the more iterations it has, the better it's going to look. And you can stop it at any time and call it done. All right, RenderMan started life in the mid-'80s, actually, when Steve Jobs took over the company. Pixar was originally a spin-off of ILM, Industrial Light Magic. And they wanted to go do motion pictures. George Lucas was like, nah, I'm good. Oh, I'm sorry. Pixar wanted to do animated movies. George Lucas wanted them to be visual effects. And, you know, they said, nah, that's all right. So they found some investors. George Lucas sold Pixar. Steve Jobs bought it. And they started to make it into its separate company. They started to experiment. One of the first movies they did, the shorts they did with Wall-E D. I don't know if anybody's ever seen that. If you haven't, you should definitely look it up. That was done all without an interface. That was in the days before we had what we call GUI interfaces, graphical user interfaces. So it's amazing that they could get that done and have it look as good as it did. But the possibilities were there. Pixar rolled out a non-commercial version for schools about 4 years ago. Until then, it was only commercial usage. You had to pay for it. And it was always, compared to other software, it was always fairly reasonable. But unless you had a lot of horsepower to run, it generally didn't run all that well. If you were trying to run it at home on your little, you know, single core Celeron computer with, you know, a gigabyte of RAM. All right, so most modern renderers were built with ray tracing in mind. Ray tracing, global illumination, all the things we kind of take for granted. Global illumination just means that it calculates bouncing energy, light waves from one surface to another. It tries to mimic how those rays would bounce from surface to surface before they run out of energy. Old systems didn't have any kind of global illumination. It was light. You had to add a whole bunch of lights to make up for what we consider bounce light. Most of the light that we have in here, in our room, is, for the most part, unless you're sitting directly under a light, it's bounce light. And even in this instance, you're still getting a lot of light that's bouncing out of the light outlet. But you go over to any of the corners of the room, even up here, out of the direct path of direct light, there's still enough illumination. Enough light bounces around in here naturally. So it uses what we call adaptive or fixed sampling. Anytime you're trying to render something, you have to sample the scene to figure out what's in it. Sampling is just a way of looking at a scene and figuring out what to work on. And adaptive sampling uses what's called contrast-based rendering and path tracing to figure out what to do. So, adaptive sampling versus fixed, your scene is broken down into pixels. Fixed sampling means that every single pixel or surface point gets measured the same way. Adaptive means that we've got kind of like a mini AI in it. So for example, the projector screen up here with my slide. Right. All the areas that are in white, right around here, in this area, is there much difference in this pixel here, or this pixel here, or this pixel there? No. They're pretty much all the same. So adaptive sampling is going to look at this and go, you know what? I can group these pixels together because there's not much difference in them, and I can sample them as a unit rather than individually, because I'm going to get the same result. Whereas if I come down here next to where there's type, the pixel next to the parentheses here, the white pixel is going to be different from the dark pixel that makes up the parentheses right there. That would be cause for the renderer to go, you know what? Those two pixels are different. I need to sample that area more because there's more contrast there. I detect a difference between this pixel and that pixel. So I'm going to sample this more than these pixels here. And it goes through and looks at the entire scene the same way. It looks for areas where it can kind of group pixels together to save render time, or areas that need to have more sampling to be able to define it a little bit better. Now, RenderMan uses IPR, just like Arnold, V-Ray, iRay. They all use IPR. That means they run and update constantly until you tell them to stop. RenderMan's got some advanced features. It's got a thing called path tracing, where it traces the path from the camera to a surface point, and then from the surface point to the light. And that way, it only calculates what the camera can see rather than your entire environment. Because anything outside of the view of the camera, you don't care about. You only care about what's inside the camera. It uses this thing called VCM, which is bidirectional. That's a little additional feature that sends out rays from the camera and the light, so in hopes that the points would converge sooner. The camera could find the light can find the camera sooner if you send out points from both directions. Takes a little bit longer, but it's used mainly to calculate things that are very hard, like caustics. You guys can all see that little shimmering effect as light goes through my bottle around here. Okay, you need VCM for that to be able to calculate, because a single path tracer would take forever to find that. I've got a really good video we're going to watch after break on Disney, and they did kind of a 1940s homage to path tracing. Heck, we'll watch it now, since we're talking about path tracing. All right, so all in all, that is a pretty good basic explanation of how ray tracing and path tracing work. So the camera is the one that emits the rays. Again, so that we are not calculating anything that's not seen to the camera. All right, let's go back to where we were. Right here. So path tracing, we're talking about render man, global illumination, caustics, and this thing called image-based lighting. This is where we can use what is called a high dynamic range image to get light information from. High dynamic is different than a regular old JPEG. High dynamic contains all kinds of embedded light information that may not be visible to the human eye. What happens is it uses a 32-bit image format, and it takes value information from there and translates that into light information. We also get color off of it as well. We'll get into that when we get into lighting and using image-based lighting. All right. So basically, rendering with any 3D package, we're taking polygons, turning them into pixels. We're taking a three-dimensional image or scene and breaking it down into 2 dimensions. Yes, I know we have stereo cameras, we have 3D glasses, 3D movies you can go see, but to be honest, they are still just cheating the eye. They are still 2-dimensional images meant to have an environment look 3-dimensional. So the purpose of rendering, to produce the highest quality image in basically the least amount of time. Remember, time is equal to money. When we talk about rendering being expensive, we're talking about time. And again, time equals money, especially when you're out working. But all in all, we are still describing light and shadow and how it interacts with a surface. Right, a couple of quick examples. Scanline rendering, very fast. Limitation. We are not ray tracing, we are not path tracing. We are simply looking at an object. If light can't get through the object, it is opaque, it creates a shadow. Even if the object looks transparent, light still can't get through the surface. Think of it as a map. These shadows are shadow maps. They're called depth map shadows. They do not have soft edges to them. They are basically, if an object blocks the light, it creates a shadow in the shape of the object. Right? Renders very fast. We don't get accurate refraction. We don't get to see light bend as it passes through a surface. We don't get transparent shadows. We don't get reflections bouncing around. But like I said, this can happen in real time. Here, We're using ray tracing. Right? We can see light bend or distort as it passes through this hourglass-shaped bottle. Right? It kind of bulges in the middle. We get transparent shadows, we get color in the shadows, we get reflectivity. It bounces around. More expensive, but worth it. So for our class file formats, we are going to be using what is called the Open EXR. EXR is a high dynamic range image format. A little bit better than some of the other formats. Way better than a JPEG. There are two different versions of this you'll find. There's something called half and full, or float, depending on what program you're using. Half is 16-bit. Float is 32. 32, that just means that it has 32 decimal places in order to calculate something. For our purposes, half works. Our image sizes, we're not doing full frame 4K images for film. Right? We're doing small renders for school to experiment and learn. There's no reason to make your Macs melt. So, for our size and file format, 16-bit or half EXR works perfectly well. Half will probably work well all the way up to Blu-ray, 1080p. Anything that big or larger, you're probably going to need to have more information in it. But for us, half works perfectly fine. Fortunately, that is the default in RenderMan. So you don't have to worry about it too much. But in general, if you're going to another program, if you're going to Arnold, you probably want to go 16-bit too. You don't need the full 32, unless you're doing super big sizes. Images are, for our purposes, RGB. Red, green, and blue channels. Each channel has 8 bits of information. 8 times 3 is 24. 24-bit images. Commonly what you get out of your phone, out of a camera. Right? It roughly gives us 16.5 million colors. Perfectly acceptable for production. All right, image size is always given in width and height. So if somebody says to you, I want a 720 by 486, it's going to be 720 pixels, and it's always going to be height second. So it's always width by height. If you're doing standard formats like HD, they may just say HD 540, HD 720, HD 1080. That simply means it's an aspect ratio. 540 would be 960 pixels wide, 540 high. 720 would be 1280 wide, 720 high. 1080 would be 1920 wide, 1080 high. That's Blu-ray. Resolution, how many pixels can we cram into a given area? The more pixels you can stuff into that area, the better the resolution, the better your edge quality, the better the appearance. Anybody here ever watch TV off of an antenna and not cable?
Yes.
Okay, antenna, had a curved TV set. Put your hand over it, you could feel the radiation. All right, that was an analog picture signal whose resolution was 640 by 480. You could have a big TV, but you still got 640 by 480 resolution. It wasn't until the 1990s that we came out with digital signals. We basically did away with the analog signal, broke our signal up into zeros and ones, made the bandwidth very small, and we could consequently get a little better resolution. So digital TV came out. That resolution was 720 by 486. All right, before Blu-ray, what was the best quality video you could get?
Laserdisc,
Something better than Laserdisc.
DVD.
DVD, yeah. The only thing that made DVD better was it was true digital, whereas laser, it looked better, but it was still analog. All right, before DVD, that was VHS, yeah. Be kind, rewind, before you turn it back to the video store. And it was usually horrible. You get in there, it was all grainy and jittery, and the heads got dirty on your VCR player, and you had to clean them with this device from another planet. You had to demagnetize the heads because all the tape was magnetized. It was a mess. So DVD quality was 720 by 486. That was digital quality. And then Blu-ray came out, and that, actually we had 720p come out first. That didn't last long. Blu-ray came out. That was the standard. Give you an idea, in old school Hollywood, 35 millimeter motion picture, that's not the lens aperture or the lens focal length, that was the actual size of the film plate itself, 35 millimeter, that was 2K, was basically 2048 by 1556. So if you were a matte painter or a compositor and you had to do a set extension or paint a background, they said, give me a 2K plate. Right. A couple years ago, it was 4K. Now it's like 6 or 8, whatever it happens to be now. So, bigger file sizes, longer render times. Right. Now, in CG, our goal is to get the best quality. You know, a computer can give you almost perfect quality because it uses pixels. And for a computer, it just turns one off or it turns one on or it changes the color. But the thing is, pixels are what shape? Square. They're Legos. So Legos are really good at straight lines and right angles. What happens when you want to make a diagonal line? What do you get?
Jagged points.
You get stairs. You want to make a curve? What do you get? You get stairs. So an algorithm was developed called anti-aliasing, which basically allows us to look at the path that our pixels are in and says, oh, I see you're trying to make this diagonal line here. You got a lot of gaps in here. I can come in and I can fill in with some various shades of gray and make this look a lot smoother. So if you kind of squint with your eyes, the one on the right looks a lot smoother. So anti-aliasing is designed to minimize that kind of jagged, rough edge that you see occasionally. Now, think about anti-aliasing. That's done by a couple of different ways. One is by doing what's called a filter on it. If anybody's ever worked in Photoshop, you know that there are sharpen filters and blur filters. And a blur filter, just depending on how you use it, will just kind of apply, if you use it subtly, a smooth kind of softening of your image. And all renderers apply basically a filter to your rendered image to soften it a little bit. That helps with the anti-alias. Another thing that helps is that when we go to sample, we don't just sample a pixel with one sample, we sample a pixel in multiple places. So think of your pixels kind of like a large rock, and your samples as sand. The sand is a lot more granular than your rock. And we use the sand to get into the areas and measure, or we are sampling, to measure all around a pixel. So we can figure out what's above it, what's below it, what's on the right of it. Because if you look at this unaliased or unanti-aliased, you can see on the right side, diagonal and above it, it's white. To the left, diagonal, it's dark. So having that information helps, being able to look at it from more than one direction in more than one place. It allows us to create a lot more accurate image. Does that kind of make sense? Questions? Now, the way RenderMan works with sampling is, kind of imagine on the beach a sandcastle that you built near the water. All right? Think of that sandcastle as aliasing. And every time the water goes over it, it kind of washes away some of your sandcastle, right? Kind of washing away noise. Think of every wave that comes over as sampling. So in order to get that sandcastle to be back nice and smooth on the surface of the sand, it's going to take several waves to come by and wash it so it's nice and level. That's kind of the way aliasing works. It washes waves of samples over the scene. It looks at the scene. Some pixels will be sampled and finished, others won't. It'll come back and wash it again. The pixels that weren't finished will be closer to being finished, and it just keeps doing it until it reaches the parameters you give it. Till it stops because you've told it to sample that much. The whole idea is lots of small samples a lot of times is better than big samples a few times, which is what older renderers were built on. That makes sense? Questions? All right, so